Good morning. Myself, Mr. Dibyendu Mondol, Assistant Professor of Greater Kolkata College of Engineering and Management under GIS Group. Today, I am discussing about thick cylinder. This is the class of solid mechanics. This is my lecture number 1 of module 4. Finally, the video is uploaded in YouTube, and if you face any problem, you can contact anytime through mail or through mobile phone or whatever it is. Okay, let's start. Now we start. Today I am discussing about thick cylinder and spheres. First one, actually the cylinder, in the last chapter we have mentioned that if the ratio of thickness to internal diameter of a cylindrical shell is less than about 1 by 20, the cylindrical shell is known as thin cylinder. Okay, ratio of thickness to internal diameter of a cylindrical shell is less than about 1 by 20. The cylindrical shell is known as the thin cylinder. For them, it may be assumed with reasonable accuracy that the hoop and longitudinal stresses are constant over the thickness, and the radial stress is small and can be neglected. If the ratio of thickness to internal diameter is more than 1 by 20, then cylindrical shell is known as thick cylinder. The hoop stress in case of thick cylinder will not be uniform across the thickness. Actually, the hoop stress will vary from a maximum value at the inner circumference to the minimum value of at the outer circumference. Stresses in a thick cylindrical shell. Okay, stresses in a thick cylindrical shell, one is the R1, another one is the R2. R1, that is the internal radius. Okay, thick cylinder subjected to internal fluid pressure. One is the internal radius R1, another one is the external radius R2. Okay, and the length of the internal radius R1, that is equal to L. Now take a longitudinal section XX and consider the equilibrium of half of the ring of figure 18.2 as shown in the figure. So here the clearly given the thickness, px, pressure, okay, another one is the sigma x, okay, and the length L. Okay, this is given. So first one is the bursting force. So that is equal to px into 2xl minus px plus dpx plus into 2 into x plus dx into L. So this is the bursting force. 2L into px into x minus px into x plus px into dx plus x dpx plus dpx dot dx. So 2L minus px dx minus x into dpx. So that is equal to minus 2L px dx plus x dpx. So resisting force, here the clearly given, this one is the px pressure, another one is the px plus dpx. Resisting force, that is equal to hoop stress into area on which it acts. So sigma x into 2 dx dot L. Equating the resisting force to the bursting force, you may write down sigma x into 2 dx dot L equal to minus 2L px dx plus x dpx. So sigma x equal to minus px minus x dpx by dx. The longitudinal strain at any point in the section is constant and is independent of the radius. This means that cross section remain plane after straining, and this is true for sections remote from any end fixing. As longitudinal strain is constant, hence longitudinal stress will be constant. Let sigma 2, that is the longitudinal stress. Hence, at any point at a distance x from the center, three principal stresses are acting. They are the radial compressive stress Px, the hoop or circumferential tensile stress sigma x, and the longitudinal tensile stress, that is equal to sigma 2. So, there are three stresses: radial compressive stress Px, the hoop or circumferential tensile stress sigma x, the longitudinal tensile stress sigma 2. Longitudinal strain, the strain occurs in longitudinal direction. So strain that is represented by E2, okay, E or epsilon 2, that is equal to sigma 2 by E, stress by modulus of elasticity, minus mu into sigma x by E plus mu into Px by E. So longitudinal strain is constant. So sigma 2 by E minus mu into sigma x by E plus mu into Px by E is equal to constant. But sigma 2 is also constant, and for the material of the cylinder, capital E and mu are constant. Sigma x minus Px, that is equal to constant, that is equal to 2a, where a is the constant. Now this one, another one is the sigma x, that is equal to Px plus 2a, equating the two values sigma x given in the equation. So Px plus 2a, so that is equal to minus Px minus x dpx by dx. Okay, so x dot dpx by dx, that is equal to minus Px minus 2a, so that is equal to minus 2Px minus 2a. So dpx by dx, that is equal to minus 2Px by x minus 2a by x, that is equal to minus 2 into Px plus a divided by x. So you may write down dpx divided by Px plus a is equal to minus 2 dx by x. Integrating the above equation, we got log e Px plus a equal to minus 2 log ex plus, actually log x base e plus log b base e, where log b base e is a constant of integration. So the above equation can be written as log Px plus a base e equal to minus log x square by x square base e plus log b base e. So you may write down log e b by x square. So Px plus a, that is equal to b by x square. Okay, so Px is equal to b by x square minus a. So substituting the value Px in equation 4, we get sigma x, that is equal to b by x square minus a plus 2a. So b by x square plus a. This equation gives the radial pressure and equation gives the hoop stress at the radius x. These two equations are called Lehm's equation, very important. Actually Px, that is equal to b by x square minus a. Sigma x, that is equal to b by x square minus a plus 2a, so that is equal to b by x square plus a. The constant a and b are obtained from boundary condition, which are at x equal to r1, Px is equal to P0, or the pressure of fluid inside the cylinder, and at x equal to R2, Px is equal to 0, or atmospheric pressure. After knowing the value a and b, hoop stress can be calculated at any radius. Okay, hoop stress. Another one, alternating method to finding the stress. In case of thick cylinder, due to internal fluid pressure, the three principal stresses acting at a point are: one is the radial pressure, radial pressure which is compressive. Okay, radial pressure which is compressive. Another one is the circumferential stress or hoop stress which is tensile. Okay, and longitudinal stress which is also tensile. Okay, if E1 that is equal to circumferential strain and E2 that is equal to longitudinal strain and ER that is equal to radial strain. তাহলে epsilon 1 that is equal to circumferential strain, epsilon 2 that is equal to longitudinal strain and epsilon r that is equal to radial strain. In case of thick cylinder, it may be assumed that longitudinal strain is constant, which means that cross section remain plane after straining. Consider a circular ring of radius r and thickness dr. Due to internal fluid pressure, the radius r increases to r plus u and increase in the thickness dr, that is b du. Okay, in case of the thick cylinder, one is the E1 is the circumferential strain. Okay, E2 that is the longitudinal strain and ER that is equal to radial strain. Okay, in case of thick cylinder, it can be assumed that longitudinal strain is constant. Okay, now initial radius is equal to r, whereas final radius is equal to r plus u. Okay, now circumferential strain that is equal to final circumference minus original circumference divided by original circumference. So 2 pi r plus u minus 2 pi r divided by 2 pi r. So final circumference, so 2 pi r plus u minus 2 pi r. So that is equal to 2 pi u divided by 2 pi r. Okay, after calculating, actually numerator r and denominator r cancel, so that is equal to u by r. So if E1 that is equal to u by r, now original thickness of the ring that is equal to dr. So final thickness of the ring dr plus du. So radial strain that is equal to final thickness of the ring minus original thickness divided by original thickness. Okay, so dr plus du minus dr by dr. So that is equal to du by dr. So ER that is equal to du by dr. So radial strain ER, the circumferential strain, the longitudinal strain and radial strain in terms of stresses and Poisson's ratio are also given by E1 is equal to sigma 1 by E minus nu into sigma 2 by E minus mu into P divided by E. So sigma 1 by B minus mu into sigma 2 by E plus mu into P divided by E. So E2 epsilon 2 that is equal to actually strain sigma 2 by E minus mu into sigma 1 by E plus mu into P by E. And another one is the ER, if epsilon r, so that is equal to minus P by E minus mu into sigma 1 by E minus mu into sigma 2 by E. So equating the two values of circumferential strain E1 given by the equation, also equate the two values of radial strain ER is given by the equation. So u by r, so that is equal to sigma 1 by E minus mu into sigma 2 by E plus mu into P by E. So du by dr, so that is equal to minus P by E plus minus mu into sigma 1 by E minus mu into sigma 2 by E. Let us first eliminate u from the equation 6 and 7. First one, equation, from this equation you have to eliminate u. So u is equal to sigma 1 by E minus mu into sigma 2 by E plus mu P by capital E into R. So differentiating the above equation with respect to R, we get du by dr that is equal to sigma 1 by E minus mu into sigma 2 by E plus mu P divided by E plus R by E d sigma 1 by dr minus mu d sigma 2 by dr plus mu into dp by dr. So sigma 1, sigma 2 and p are function of r. Equating the two values of du by dr given by equation minus p by e minus mu into sigma 1 by e minus mu into sigma 2 by e. So that is equal to sigma 1 by e minus mu into sigma 2 by e plus mu into p by e plus r by e d sigma 1 by dr minus mu into d sigma 2 by dr plus mu into dp by dr. Now from this equation actually minus p, if you substitute, actually if you calculate minus mu into sigma 2 minus mu into sigma 1, that is equal to sigma 1 minus mu into sigma 2 plus mu into p plus r into d sigma 1 by dr minus mu into d sigma 2 by dr plus mu into dp by dr. So 0, that is equal to p plus mu into sigma 1 plus mu into sigma 2 plus sigma 1 minus mu into sigma 2 plus mu into p plus r d sigma 1 by dr minus mu into d sigma 2 by dr plus mu into dp by dr. So if you take common p1 plus mu plus sigma 1 plus mu plus r d sigma 1 by dr minus mu into d sigma 2 by dr plus mu into dp by dr. So if you take common p plus sigma 1 plus u mu plus r into d sigma 1 by dr minus mu into d sigma 2 by dr plus mu into dp by dr. To find the value of sigma 1 in terms of p, the value of d sigma 2 by dr must be substituted in the above equation. So longitudinal strain is given by the equation E epsilon 2, that is equal to sigma 2 by E minus mu into sigma 1 by E plus mu into p by E. So since longitudinal strain is assumed constant, so its differentiate with respect to r will be 0. So differentiating of the above equation with respect to r, we get 0 equal to 1 by E d sigma 2 dr minus mu into d sigma 1 by dr plus mu into dp by dr. So 0 equal to d sigma 2 by dr minus mu into d sigma 1 by dr plus mu into dp by dr. So that is equal to d sigma 2 by dr equal to mu into d sigma 1 by dr minus mu into dp by dr. So substituting the value d sigma 2 by dr in the equation 9, we get 0 is equal to p plus sigma 1 plus mu plus r into d sigma 1 by dr minus mu into d sigma 1 by dr minus mu into dp by dr plus mu into dp by dr. So p plus sigma 1 plus mu plus r d sigma 1 by dr 1 minus mu square plus mu into dp by dr 1 plus mu. So p plus sigma 1 plus mu plus r 1 minus mu square d sigma 1 by dr plus mu r 1 plus mu dp by dr. P plus sigma 1 plus mu plus r into 1 plus mu 1 minus mu d sigma 1 by dr plus mu r 1 plus mu dp by dr. So you calculate 0 equal to, after calculating 0 is equal to p plus sigma 1 r 1 plus 1 minus mu d sigma 1 by dr plus mu r dp by dr. So for equilibrium of the element, resolving the forces acting on the element, we get P plus dP R plus dr del theta minus P into R del theta minus plus 2 sigma dr sine del theta by 2 equal to 0. Del theta is small, so sine 2 theta del theta by 2 is equal to del theta by 2. So the equation becomes P plus, actually this is the diagram, radial diagram. Okay, P plus this one, when you follow the equation, so this is the radial diagram, this one del theta. So P plus del P R plus dr del theta minus, okay, minus PR del theta 2 sigma 1 into dr into del theta by 2. So after calculating, if you calculate this value, so d sigma 1 by dr that is minus dp by dr equal to 0. So this is the, in this equation we get, let us find the value from this equation. Actually sigma 1 minus p, that is equal to 2a. Okay, sigma 1 minus p, that is equal to 2a. Okay. Okay, thank you. So my lecture video is uploaded in YouTube. If you like it, you have to subscribe my channel, and if you face any problem, you may contact anytime through mail or over telephone. Okay, thank you.